Okay, so in chapter 4, we're going to be covering a lot of things about reactions and solutions and things of that nature. So let's just get into it. So the first thing we cover is the different types of solutions. So there's polar solutions and non-polar solutions. Those are the two main types of solutions. And by solution, I just mean it's a mixture of different chemicals. That's really what it is. And solutions could be, it could be gas solutions, it could be liquid solutions. You're good, Isaiah, don't worry. So it could be liquid solutions, it'd be gas solutions, and there could be solutions with solid in them, and liquid and solid, and a mixture of all different states. But regardless, so you have polar and non-polar, right? And what polar is, and there's a term that, or there's a phrase that one of my students years ago said, it was like, polar bears like water. So yeah, it's exactly it. So polar bears, and the word polar itself, it means water-liking. And it means something that has an unequal distribution of charges, more specifically. But what that means is, just like water molecule, which is written right here, it has a written, where's the mouse? There we go. So just like the water molecule, which is right here, polar solutions have this unequal distribution of charges. Now, did we talk about electronegativity last week? No? Or 2 weeks ago? No? Okay, well, basically, that should have came before this, but whatever. So electronegativity basically means it has to do with whether an element is it's kind of in relation to if it's a cation or an anion, right? So things like metals and things like hydrogen, which is on the left side of the periodic table, which when it becomes an ion tends to be +1. Those tend to have a very low electronegativity. They have a low number of valence electrons, maybe 1, 2, or 3, or even 4, and they tend to lose those valence electrons. If they lose those electrons, you could say they have more of a tendency to get rid of electrons. They don't like electrons. So electronegativity is a trait of an element that measures how much an element likes electrons. So those elements would have very low electronegativity, but the ones on the right side of the periodic table, such as the nonmetals, and not the noble gases. Noble gases don't have any electronegativity. They're happy, like we've talked about. But things like oxygen, fluorine, chlorine, they have a high electronegativity, meaning they like to take in electrons. And that makes sense based on what we learned about ionic bonds, where the nonmetals tend to gain the electrons that the metals lose. So this is the same idea, but instead of talking about metals and nonmetals in ionic bonding, we're talking about two nonmetals or two or more nonmetals in covalent bonding. So that's the case with water, where you have this unequal distribution of charges. You have this unequal distribution of charges where the oxygen, since it likes the electrons a lot, it pulls the electrons in the covalent bond towards it, becoming partially more negative, since it will have more of an electron density after the bond is formed. And vice versa, the hydrogens will have less of an electron density. So this phenomenon of the difference in electronegativity between elements in a covalent bond forms this idea of polarity. So that's what polarity is. It's that formation of the unequal distribution of charge, and usually in covalent bonds. And this polarity facilitates a polar solvent's ability to dissolve something. And we'll talk about exactly how that happens in the next slide. So then you have, that's one type of solution where there's charges involved, there's differentials in charges involved, and that differential in charge facilitates the dissolution of different compounds, whether it be a salt, a sugar, or an acid or a base, things like that. But then when you have nonpolar solution, which is the second type, it really is the opposite. Really, there's no differential, or very little differential in electrons in the bonds. Examples of this would be any carbon chain containing thing like fatty acids, lipids, oils, greases, things like that, that usually have like a lot of organic molecules. So if you ever take organic chemistry, you'll be doing experiments, or if COVID is gone, you'll be doing experiments with methane, benzoic acid, which is a little bit of both. And you have a lot of these organic molecules are going to be nonpolar, meaning the difference in electronegativity is not great between the elements. And also they're very symmetrical molecules too, so there's no unequal pulling of electrons. So that's what nonpolar is. And also another thing is there's a whole range of polarity. So it's not only that something could be polar or nonpolar, something could be weakly polar. You could, if you picture, you could have a huge molecule of different covalently bounded things where one half of the molecule is polar, the other half is nonpolar. That's totally acceptable. So there's a whole range and a whole spectrum of polarity. Things like methanol, for example, methanol is a CH3 group, a methyl group, which is not very polar. And then it has an OH on the end, which is very polar. So the whole molecule itself is considered to be polar because it has half a polar part. But then when you increase the amount of CH3 groups or carbons, you get ethanol, propanol, butanol, and then the longer you go, the more nonpolar it becomes because you're adding more nonpolar groups to it. So there's a whole spectrum of polarity. Okay, so hydration, let's just look at hydration. So here is exactly how something that's ionic likes to dissolve in water. So you have, the way I like to describe it is the physical attacking of the water molecules, well, the charge facilitated attacking of water molecules to the ionic substance that is being dissolved. So here's an example. Let's say this is NaCl. You have the, and this is actually wrong, the sizes. Cl is very small and Na should be really big. But regardless, you have the pluses and minuses. They're all in a big crystal, let's say. Then when you drop the salt crystal into water, you mix it up. That speeds up the molecules of water, which then attach based on their charge to the oppositely charged molecule, such as the positive ends of the water attach to the negative ends of the chlorine, and the negative ends of other water molecules attach to the positive ends of the sodium, like you do here, like you see here. Then the water kind of goes deep into the structure, kind of rips it apart. Ion by ion, rips it apart. And that's how dissolution happens. So this is how dissolving of electrolytes occurs. So it's the physical ripping apart of into positive and negative charges, which is called dissociation, or another term is ionization, because they're becoming ions. Before, the NaCl crystal is not charged at all. But once you put water in there and split everything else into charges, split the Na and the Cl into charges, then each of those specific molecule or each of those specific complexes, let's say, has a charge based on the ions. So that solution, after it's done dissolving, can now conduct electricity because it has positive and negative charges in it. So we call it an electrolyte. So yeah, we talked about that. Then you have things that are, we call them non-electrolytes, which we're going to see all the terms in a minute. But you could also have a dissolution of compounds that don't dissociate into ions. Things like that are going to be sugar, and ethanol is a good example of that. So ethanol is, here's the structure of ethanol. So you have a CH3, you have a CH2. Where is my mouse? It keeps disappearing. Yeah, you have a CH3, you have a CH2, and then you have an OH, which is very polar. This part's not really polar, but the overall polarity of the molecule is pretty polar, right? And so that will interact with other water molecules in a polar solvent, such as water, and it will be dissolved pretty well. So it's considered to be polar. Not as well as something like NaCl, but still pretty well. And then you have, but the thing is, the key thing, when it dissolves, it's not going to be ripped apart. So the OH isn't coming off and being split into its own ion like the NaCl is. And the CH3, CH2 is not being split off into another different group or anything. So the water molecule will just, multiple of them, will just engulf the ethanol in this case, but it will not rip it apart into ions. So it won't ionize it, but it will dissolve it. So that's what electronegativity is. We're going to be talking about the difference between ionization, either full ionization, partial ionization, or dissolving, but non-ionization, which is this nonpolar case, or this polar but not salt case, not ionic. Okay, so the makeup of a solution, you have the main two, well, the only two parts are the solute and the solvent. So the solute is the substance that's being dissolved. The solvent is whatever medium it's being dissolved in. So for water, for polar solvents, you can have water, you can have ethanol, you can have ethyl acetate, just to name a few. And then common nonpolar solvents, you have benzene, I don't know, cyclohexane, DCM, dichloromethane, and there's a bunch of them. But anyway, the solutes could be endless. They could be solid, liquids, or gases, really anything. And it's really considered to be a homogeneous mixture. So that's when you have a full incorporation, and you know when it has equal parts. And so like I mentioned before, so once you have these ionic substances like NaCl that break apart and ionize into their Na pluses and Cl minuses, you get this electrical conductivity as a byproduct of this process, which is good because you can use that conductivity to power light bulbs, batteries, and things like that. So that's due to the ions. So it's important that maybe you've seen like on a bunch of different movies where you see like somebody put in electrical on a live wire into the water and it shocks things in the water, right? That's not due to the water itself. So water itself is not electrically conductive. It's when you put ionic substances or solutes into the water. So in seawater or even lake water that's not considered salt water, there is still a large percentage of minerals from the wildlife. There's magnesium, there's calcium, there's chlorine, there's sodium, there's all these different ions in there that contribute to its electrical conductivity. So that's what we call electrolytes. So here's an example of that, where on the left here, you see many ions. So this is NaCl, something really any ionic salt that dissolves. And you see it's fully ionized and you get a bright light because that there's a large current because the electrons can jump through this medium, through this now ionized medium. Then you have few ions, which is what we call a weak electrolyte, and we'll see the terms in the next slide, but where you have a very small percentage of ionization. It's actually around 1%, maybe a little bit less of ionization. And you get a very weak signal, a very weak conductivity, if any. And then no ions, something like sugar or ethanol or methanol that would dissolve in water, which doesn't really break apart into any charges, and it won't ionize at all, and it won't have any electrical conductivity. So here's the term. So here's strong electrolyte. So the definition that should be added to this, it's not really, well, yeah, it conducts current very efficiently, cool, but more specifically, when it does 100% ionization in water. That's the key term. So for strong electrolytes, right, 100% ionization in water. It's very important. And then for weak electrolytes, you have a very small percentage of ionization. So things like weak acids and weak bases that don't really dissociate much in water, they are going to only conduct a small amount of electricity when they're put into aqueous solutions. But you can put a very low level of ionization in water. So whereas strong electrolyte is 100% ionization, every single molecule of a strong electrolyte will dissociate into its ionic components, whether it be an ionic salt or a strong acid or a strong base. So we'll talk about those examples more examples in a couple slides, but yeah, so that's that. And then for weak electrolytes, things that are weak acids, weak bases, those are really the only two things that they are. So weak electrolyte, weak acid, weak base. And I will show you a little mnemonic to know. I'll show it to you in a next slide. I'll write it down just so you can remember a quick way that no textbook has, that me and a couple of friends in college made up to actually memorize all the strong acids. And it's on my Crash Chem Instagram thing, but I'll tell you in a couple of slides. So that's weak electrolytes. They're weak, not strong, right? Then you have non-electrolytes. So they're the ones that do not break up. They have no ionic dissociation when they dissolve. But the thing is, they still dissolve. So something that's debatable is oil a non-electrolyte? Well, it doesn't dissolve in water at all. So, but it doesn't dissociate because it doesn't dissolve at all. So it's something like oil would not be a non-electrolyte. Even though it's not an electrolyte, it's a non-electrolyte is something that does dissolve in water, but doesn't ionize. So something that's non-polar, like grease or oil, doesn't have the property, doesn't have polarity. So it won't dissolve in the first place. So you can't consider it to be any of these types of electrolytes. So, interesting. All right, so going down the list of things that are strong electrolytes, are going to be soluble salts, meaning soluble ionic compounds. Now, a question you can have is, oh, professor, what constitutes a soluble ionic compound? That's a really good question. And we're going to learn about that in the next slide, about what's soluble and what's not soluble. Because not all ionic compounds are soluble. Some of them are very sparingly soluble, and some of them are not soluble at all, like silver chloride, I think. No, like silver, silver chloride. Yeah, that's one. Yeah, anything we have, we're going to learn 3 ions that are important: silver, lead, and mercury. Those are not really soluble in much. Okay, then you're going to have strong acids. So I will bomb out of this so I can write things. Okay, so, all right. So for strong acids, easy way to remember the strong acids. I still have the ink on this cool, I had a cool color yesterday. Those rainbow sparkly colors. I'll just go black for now. Okay, so for strong acids, there's a little mnemonic that me and my friends invented. So I'm going to say it, and then I'm going to write it. So it's Hickel, Hibber, High, Hino, Hicklo, Hisso. That's weird, right? So I'll break it down as I write it. And this is very important. No, I've never seen another professor teach this. I've never seen it anywhere else. So that's good to get your pen up to write this. It's important. So I'll give you an edge in identifying acids and bases, or just acids. So Hickel, HCl, very strong acid. Hibber, HBr. High, hydroiodic acid, or just HI. Hickel, Hibber, High. Hino, HNO3. Hicklo, there's actually 2 Hicklo, so it's not perfect. HClO4, that's perchloric acid. Then there's another Hicklo, HClO3, that's just chloric acid. And then Hickel, Hibber, High, Hino, Hicklo, Hisso, which is the strongest one, H2SO4. So these are the most common strong acids in chemistry. Obviously, there's more, but there's none that are there's no more ones that are simple. Like there's sulfonic acid, which like breaks the pH scale. There's like other ones that are different, but these are the main ones in chemistry that you need in undergraduate, unless you go into cutting edge research into acids and bases. But so I'll say it one more time: Hickel, HCl, Hibber, HBr, High, Hino, HNO3, Hicklo, there's 2 Hicklos, HClO4 and HClO3, Hisso, H2SO4. The thing is, if you know this, you know the strong acids and the weak acids, because the weak acids are anything not on this list. So boom, automatically from that, you can tell which acid is a strong electrolyte, which one's a weak electrolyte. So that's very important. And then for bases, there's another rule. So strong bases are also classified as a strong electrolyte. And basically, get it? So there's one rule really for the strong bases. So group 1A or 2A hydroxides, with a few exceptions like magnesium hydroxide. But in general, when you see a group 1A or 2A hydroxide, such as NaOH, CaOH2, KOH, these are going to be your strong bases. So what this means is, in any case you come into a situation where you have a transition metal with a hydroxide, that's automatically a weak base. Or ammonia, that's a weak base. So those are the key ones. Yeah. Okay, cool. Any questions on that? No? Okay. Still writing? All right, I'll move on. Oop. Okay, so we talked about this. So soluble salts. Now, we're going to go into, yes, we talked about soluble salts already. Some of them are not soluble, and we'll see that we're going to talk about a list of solubility rules that you're going to have to be familiar with. The strong acids we talked about, they have a dissociation. Here's something that's good to know. So we'll talk about HCl. HCl and HNO3, they go hand in hand. Now, so Hickel and Hino and Hiso. So these are 3 examples here, where you see when they add it to water, there's 100% dissociation of H plus and Cl minus. And in nitric acid's case, you have H plus and NO3 minus. Now, for H2SO4, it's a little different because it has 2 hydrogens. So if you're like, all right, it's got 2 hydrogens, then they both must go away, right? No. So when you do for the strong acid, for any acid dissociation, it's always 1 proton at a time or 1 hydrogen at a time. So when the first hydrogen is dissociated, when it comes off, it becomes H plus HSO4 minus. Now, technically, this HSO4 minus is still an acid, but it's not a strong acid anymore. The only one that's a strong acid is the original H2SO4. Since this is a different substance, it has different properties. It doesn't want to get rid of this second hydrogen nearly as badly. So it's considered a weak electrolyte in this case. So the strong electrolyte in H2SO4's case, it dissociates into H plus and another weak electrolyte. So that's good to know. And this is what we call a diprotic acid, meaning 2 protons, diprotic. There's also triprotic acid like phosphoric acid, but that's another story. So yeah. Okay, so, I knew I was onto something. So here's my thing. I wrote this. So I forgot I wrote this in the slides. But anyway, here it is again. So strong acids, we know. We're talking about acids a little bit more. But here they are again. So Hickel, Hibber, High, Hino, Hiclo, Hiso. Those are the strong acids. And here's how to dissociate. So there's another way of writing the equation at least. If you have whatever the acid is, HA just means these H's, whatever the A is, the acid part of it, the anion part. So you're going to add water, and then what's going to happen is, since the idea of acids is they have the hydrogen and they don't want it, so they want to get rid of it. They're called proton donors or electron acceptors. That's like the opposite. So what they want to do is they want to get rid of the hydrogen. So they're going to get rid of it to anything in the solution that can accept it. Now, in water's case, water is neither an acid or a base. It's actually called amphioteric, where it can behave as both. So what that means is whatever it's paired with in the solution, let's say water in this case is paired with an acid, it will act as the antagonist, or it'll act as the base. So what will happen is the hydrogen from the acid's like, yo, I really don't want this hydrogen right now. It will take the hydrogen away from the acid, or the water will take the hydrogen away from the acid and become hydronium, which is called H3PO, or no, yeah, H3O+. It's called the hydronium ion, like that. And then you have whatever's remaining is the anionic part of the original acid. So this is what we mean by the complete dissociation into water. It's actually not going to be free H+, as the previous equation showed. It's going to be added onto a water. The water will accept that hydrogen, and it'll become hydronium, and H3O+. So that's how that works. Any questions on that? No? Okay. Okay, so Strong bases, which we've already covered, but we'll see the actual notes on it. We have group 1A/2A hydroxides. So anything in group 1A or 2A with a few exceptions paired with an OH, one or more OHs. And it works in a very similar manner where you have the OH will dissociate from the whatever is the cation. So just like how acids don't have hydrogen and don't want it, bases will have OH and don't want it. Or in other words, they will want, another thing that they do is they want hydrogen. So in every way you contemplate it, acids and bases are the complete opposite of each other. So acids they have the hydrogen, want to get rid of it. Bases, they take in hydrogen, but at the same time, they release OH into the solution. That's something they do. Any questions on that? Okay. Okay, so weak electrolytes are really only weak acids and weak bases. So things that are like that, let's say HF is a weak acid. H2S, that's hydrosulfuric acid. H3PO4, phosphoric acid, that's a weak acid. Acetic acid is a weak acid. Anything that's not on the Hickel, Hip, or high, so is a weak acid. Weak bases, the one key weak base you should know is ammonia. So you've probably heard of ammonia before. So here's ammonia, NH3. It is the hallmark for a weak base. So you in the textbook and anywhere else, you'll see the dissociation of a weak base equation with ammonia, and it'll look like this. So H3 or NH3 plus H2O. So let's take a look what happens. NH3 is a weak base. Remember what I said about water, that water is neither an acid or a base, but it will act as one of the two depending on what it's paired with in the equation. In this case, it's paired with a weak base. So water will act as the acid. And I'll be like, oh, since you're a base, I will act as an acid. And since you want hydrogen, I will give you hydrogen. And this ammonia now becomes ammonium ion. So that's one of the polyatomic ions that you should have seen before. So ammonium. And then whatever is remaining is the hydroxide ion that is produced by the dissociation or the ionization of NH3 ammonia. So that's an example of a weak base doing that stuff. Oh, Vivian, that's a very good question. I'm assuming you're talking about acids. Yes, the number of hydrogens, does it have anything to do with this weakness? That is a great question. And the answer is actually no. So the more hydrogens an acid has doesn't necessarily have to do with its acid strength, at least for these inorganic acids. When we talk about organic acids, like acetic acid or benzoic acid, or more complicated ones like palmitic acid, and there's a lot of different types of acids that have multiple acidic groups that dissociate an H. Those, the more acidic groups you put on, the more acidic it gets, but not for these. Why? Because of electronegativity and stuff. We'll leave it at that. But so is it the good thing you should know then? That's a good segue too. In organic chemistry, there's this functional group called the carboxylic acid, which is key, and this is what it looks like. A C double bonded to an O, single bonded to an OH. That's what it looks, and this is R, some other crap. So you can put anything on the end of that. So wherever you see this group in organic chemistry, this is called a carboxylic acid. And it's a weak acid, but it represents a place in an organic molecule that has a place of deprotonation, meaning this hydrogen can come off. So the more of these you see in an organic molecule, the more acidic it generally is. So that's a good point to make. But it itself is considered a weak acid. Like lactic acid has a bunch of these. It's considered a weak acid. Citric acid, like orange juice, that's a weak acid. and it has a bunch of these. Or has one of these, I think. But okay, good questions, good ideas. All right, moving on. So weak acids, here's the dissociation of weak acids. This should be an arrow. So here's acetic acid. So it's HC2C3O2. And they're written this way because it's good to make it apparent that the beginning H, the H in the front, will be the one that dissociates when it becomes ionized. So you could have wrote it as C2H4O2, but then you don't really know the structure. So you don't know that it's acetic acid. But anyway, what happens is the same thing as we saw for ammonia, where water in this case will act as the acid because, nope, well, base is the opposite. So it'll work as the base because acetic acid is acting as the acid, even though it is weak. So what will happen is water will be like, oh, I don't care. I could either lose a hydrogen or I can gain a hydrogen. What do you want to do? Acetic acid will like, well, I'm a weak acid. I'll lose the hydrogen. And the base is like, fine, I'm okay with that. So then the hydrogen from the acetic acid becomes, or the acetic acid becomes deprotonated, meaning it loses that hydrogen. And then the water gains that hydrogen, becomes the ammonium, or the hydronium ion, and then the acetate ion that we've seen before, so acetate. So that's an example of a dissociation of a weak acid. But a key thing to remember, or a key thing to know about this, is that when weak acids dissociate, the reason why it's called weak is because they dissociate only slightly, a slight extent of dissociation. Meaning, I would say 1 to 3% at most of the acetic acid molecules dissociate. The rest of them are left as acetic acid. So most of it's not going to react. That's why I drew this double arrow. It's called an equilibrium equation. What that means is at the end of the day, after all the reaction is done, there is an equal number of acetic acid molecules becoming acetate ions and vice versa. It's actually going back and forth at the same time, but it reaches an equilibrium level. So there will be probably 97% on the left side, only 3% on the right side. But this is the level that it likes to be at because of the nature of acetic acid being a weak acid. So yeah. Okay, so that's cool. We saw that already. We saw this already. This is the production of OH by the mixing of ammonia into water. So we talked about this already. Cool, we saw that. Non-electrolytes. So things that are non-electrolytes, you're going to have polar substances. So polar meaning they dissolve in water. They have an unequal distribution of charges, but they're not ionic. There's no place for them to ionize. So they produce no ions. And a good question could be, oh, for my test, how do I know that? How do I know which one of these is ionic or not? Well, generally speaking, we know ionics are metals and nonmetals, but some of the acids ones, they have H's in the front. You see these don't. But for non-electrolytes specifically, the best way I can say it is if it has a complex looking structure, let's say a bunch of carbons, or it's written like C's and H's and O's and N's, or it looks like a complicated formula, chances are it's a non-electrolyte. And putting that information in combination with what you do know about the strong and weak electrolytes, you should be able to figure out if you were given which of the following is a non-electrolyte. You should be able to figure that out. So just bulkier structures and things that don't really have an apparent breaking point into ions. Okay, good. All right, so which of the following statements is true? If a substance is soluble, it must be an electrolyte. Is that true? No, because you can have non-electrolytes. They're soluble, but they're not electrolytes. If a substance is an electrolyte, it must be soluble. What do we think? Good, correct. Good, so yes, this is true. Because in order to have this, remember electrolyte is conductivity, it makes ions. In order for it to make ions, it has to be soluble in the first place for water to break it apart. Next one, weak electrolytes must be less soluble than strong electrolytes. Nah. Well, we know the answer is B, but the reason C is not right. So because they're both equally soluble, but just one dissociates more. Non-electrolytes are non-soluble. Not true. You have sugar. Okay, good, nice. All right, chemical reactions. We'll go over some math stuff, and then we'll take a break. All right, so chemical reactions. We know that we did balancing already, right? Last week, chapter 3. All right, cool. All right, so we know what equations look like, and we know they happen when two or more things are mixed. So we need to know some properties relating to solutions with reactions. And one of those biggest properties is the concentration. So depending on the concentration of a solution, you can figure out many things. You can figure out how well it's going to react with something, how many moles of it there are, how much of another substance you need to weigh out or to figure out the volume, to add it into this substance, to do a chemically sound experiment. There's a lot. But to know concentration is to know the SI unit for concentration, which is molarity. So that's molarity. Molarity is measured by the moles of the solute divided by the liters of the solution. So whatever the total liters of the solution is, it has to be in liters. If it's in milliliters, you just convert it to liters. And then the moles is just the moles of whatever is inside the solution. So you can think of concentration as, let's say, a percent amount almost, but it's not. It's a little bit more than that. It's just like a mole percent amount, but it's not percent. Percent's a bad word. But it's just like, well, I guess the amount of moles per unit of volume. So how concentrated something is. You can think about it like that. So you could have like, something that I do that's weird is if I have orange juice, I'm not sure, I don't think it's weird. Some people do it. They dilute their orange juice. It's too sweet sometimes, but then if you put a little bit of water into it, you dilute it. So, and it just tastes about the same. I don't know, it's college life, you know. But let's see this chat. Someone can make fun of me. Exactly. If you dilute the orange juice, the more orange juice you have. Wait, where's the chat? Where'd it go? There we go. That is weird, not weird. Thanks, Mila. Nasty. Thanks, Zach. All right, you guys get extra credit. Just kidding. Matt gets extra credit. Everybody else doesn't. All right. So weird or not, the example still makes sense because originally you have the orange juice molecules, and let's just say orange juice molecules, right? So you have the orange juice molecules in a cup. If you dilute it, and that's considered a high concentration, you have, let's say, 1 mole in that let's say 1 mole in 1 liter. If you dilute it and put the same, or you put another liter of water in there, you now have that 1 mole dispersed into 2 liters. So we dilute it. The molarity will change. The molarity will decrease, but the volume will increase because we're diluting it across a larger volume. But so that's an example of that. Yeah, the 21 and over example, you can dilute your drinks. You can with like a chaser or something. But whatever, you guys are not old enough for that. But anyway, oh, there's the answer. So whatever, we'll do the math. So calculate the molarity of the solution in which a 184.6 milligram sample of potassium dichromate is dissolved in enough water to make 500 milliliters of solution. Okay, so let's do it. So calculate the molarity, blah, blah. All right, so you have 184.6 milligrams. So immediately off the bat, we want to convert this to grams. So it'll be 0.1846 grams of potassium chromate. So to figure out the moles of potassium chromate, we need to know that because molarity, the big M, is equal to moles divided by your liters. So what is the molar mass of potassium chromate, dichromate? 294.2. That's probably right. Should be pretty big. So we know that the molar mass is 294.2. So now we divide that, and what do we get? Should be really small. Oh, any molar mass? Yeah, I told you guys to do it. I'm kidding. No, it's okay. I'll look up. Tennessee. Oh, that's good. What'd you get for moles? Sounds good. 6.27 times 10 to the negative 4. Yeah. Perfect. Oh, not over 500. Yeah. Okay, good. James, did you get that too? For the moles? Okay, cool. Good. All on the same page. All right. So when you figure out the moles, so you're doing the grams divided by the molar mass, we get 6.27 times 10 to the 4th moles. And we're dividing that moles by the liters of the solution, which we know from the problem is 0.5 liters or 500 milliliters. And you get, it should be like 12 times 10 to the 4, which is 1.255 times 10 to the negative 3, about. So there you go. Okay, any questions on that? Anybody online or in person? No? Pretty good? Okay, cool. All right, so next, we'll do one more. So calculate the molarity of a solution prepared by dissolving 1.56 grams of gaseous HCl in enough water to make a 26.8 milliliter solution. All right, so same thing. We're doing our moles divided by our liters. So moles of solute is going to be your 1.56 grams of HCl divided by the molar mass of HCl, which hydrogen is about 1, Cl is 35.45. So you have 36.45 grams per mole. And you do the math for that. 1.56 divided by 36.45. You get 0.0428 moles. And we're going to divide that by the total volume of solution, which is 26.8 milliliters. But to get it into liters, it's 0.0268. 0.0268. And we get about 1.6, but 1.597 molarity, but sig figs, 3 sig figs, all over the place, 1.60 molar. So the way we say it is, it's a 1.6 molar solution. That's like the terminology. Okay, cool. Any questions on that one? Pretty good? Pretty easy formula? So that formula, if you guys were talking about formulas before, you're going to have to know that one. So that one's not going to be given. All right, nice, good, good, good. That's another one. That's just the same thing, just calculating moles. So you're going to have the molarity, basically plug and chug. You're going to have the molarity, you're going to have the liters. You'd multiply them together to figure out the moles. So we're not going to cover that one here, but same exact thing. Okay, so now, here we go. Example, orange juice and alcohol. I talked about those already. Wow, I was ahead of myself when I made this. But anyway, so dilutions. So there's a formula for dilutions, even though we did talk about them a little already. Now, when you dilute something, you have originally, you have a higher concentration at a lower volume. When you dilute it, you increase the volume of the solvent, so the volume of the entire thing increases, but the amount of solute stays the same. So if you increase the volume and you keep the amount of solute there, what's going to happen to the concentration? Will it go up or go down? Down. It'll go down when you dilute. So that's exactly what this formula says. This formula shows the inverse proportionality of the concentration with the volume when you dilute something. So if you look at the concentration, or look at the formula, M1V1 equals M2V2, the initial molarity has some initial volume. When you dilute it, the initial volume will become higher, or sorry, the volume 2, the final volume will become higher, and the final molarity will become lower, because that same solute is spread across a larger volume. So that's what this dilution formula represents, the inverse proportionality. Now, we're going to be seeing in this class, and I'm sure in your other classes, physics and math, a lot of inverse proportionality formulas that are the same thing. You have variable one initial times variable one initial times variable two initial equals variable one final times variable two final. That's the key, like the hallmark formula for inverse proportionality. So we're going to see that when we get to Boyle's law in gases. We're going to see that a couple other places too, but that's really how it works. In physics, you see that as well. With like kinetic energy, I guess. 1/2 mv squared. And momentum. Stuff like that. Someone said something in the chat. Pretty much every conservation law. Yeah, exactly. So let's do some examples with that. No, we're not. Yeah, we are. Here we go. So what is what volume of 16 molar sulfuric acid? All right, stop there. 16 molar sulfuric acid, that will like burn through your glove. That will go right through your skin. That will burn like hell. So that is very concentrated. Now the stuff, if you guys were doing lab, you'd be, and you dealt with the acid-base lab, it would be maybe 1 molar hydrochloric acid, which, or 1 molar sulfuric acid, which is still, it will still heavily irritate your skin, at least the surface of your skin, and your eyes, it would burn like hell. But and even then, you're supposed to take precautionary wear your PPE. But for 16 molar, that's hardcore. So how much of a 16 molar sulfuric acid stock must be used to prepare 1.5 liters of 0.1 molar sulfuric acid? Now, the 0.1 molar is more of like what you would use in general chemistry. But to prepare that 0.1 molar, the TAs, and which was me in my graduate school career, I have to deal with the big vats of 16 molar and try not to spill it anywhere, and then make enough dilution or make enough volume to have for the whole class of the diluted version, the 0.1 molar. So let's do this. Let's write the formula down, which is M1V1 equals M2V2. And the most important thing is to, obviously we're plugging and chugging, but we want to make sure that our plugging is in the right place before we chug. So the volume one, or the volume has to be associated with the correct concentration. So there's different ways to do it. I do it as I read it. So I would look at what volume. Oh, it's asking for volume, V1, whatever. Of 16 molar, okay. So I'm gonna put 16 times V1 equals, must be used to prepare 1.5 liters of 0.1 molar. So I'll put 0.10 times 1.5, and then you would solve V1 from there. And it doesn't matter if it's V1 or V2. The most important thing is that our unknown volume is associated with our 16 molar, and our 1.5 liters is associated with our 0.1 molar. So you have to be conscious of the sentencing, of the phrasing, where you have the volume and the molarity in the same sentence. They go together. Usually it's whatever volume of a specific concentration. So what you would do here is divide the right by 16, and you'd get a number, obviously. So what number do you get? I don't know. Let's see. 0.1 times 1.5 is 0.15 divided by 16 is 9 point, or we could just do 0.009 liters. So 0.009 liters is approximately 9 milliliters if you multiply by 1,000. So you would need 9 milliliters into 1.5 liters of the 16 molar to get to a 0.1 molar. So yeah, that's a pretty big dilution. And so a good question that comes up is, can you undilute something, like concentrate something more? And the answer is yes. So we have certain ways in chemistry and in biology to further concentrate a solution. Now, it's very difficult So, but there's different ways to do it. So in the chemistry way, let's say we had a solution of, well, like I guess like salt water. We use very, very simple salt water. So if you boil out the water to a certain level, the salt's not going to go out with it. So it'll just be, you'll just be getting rid of the solvent. The solute will stay. So you'll be further concentrating salt water by boiling. That's a very easy way of doing it. If you have some solutions, some solvents that are very, very high boiling point, what you can do is increase the pressure, or decrease the pressure, which will make them boil a lot easier. And you can do the same thing under a very controlled environment. And this is called the rotovape, which is a technique, which is an instrument that you expose it to a vacuum, and you have a water bath with like only 30 or 40 degrees Celsius, like very warm water, but not hot. And the organic solvent that usually has a boiling point of even like 200 degrees Celsius, that boiling point will drastically be reduced in a vacuum. So using only warm water, you can boil out that solvent and still have whatever the solute is remaining there. So it's a pretty cool technique. So that's in chemistry. In biology, you can concentrate a solution. The way I do it is you could do it by mass. So in a biological solution, let's say we have cells, and let's say, or proteins or macromolecules, molecules that are much bigger than solvent solvent particles, like much bigger than water. So what you could do is put them in this little vial that has a membrane on it. And that membrane is semi-permeable by mass. So it only lets, what that means is it only lets small mass particles or smaller particles escape. But bigger particles like the cell, like the proteins, don't escape. So what happens is if you take that vial, put your sample in there, and you put it in a centrifuge, and you spin it really, really fast, what will happen is it will force the solvent particles that are very small and can go through the membrane into a secondary chamber on the bottom. So it will force them out of your solution into the membrane or into the second container. And then what's left in the initial container is your proteins, your cells, everything that didn't go through the semi-permeable membrane with some solvent that's left over. And you can actually, based on the amount of time you centrifuge it, calculate how much you want left over and set it for that amount of time. So that's one way to concentrate things. It's a really cool process. But anyway, so I digress. Okay, so let's do one of these. This is the first one. So let's do another dilution and then we'll move on. So describe how you would prepare 2 liters of each of the following solutions. So, all right, how would you do that? Now, you have the first one, you have 0.25 molar of NaOH from a 1 molar NaOH. Okay, so we have, we're preparing, our end goal is 2 liters. So we can make V2 our end goal. So another way you can write these plug and chugs, if you're not comfortable with just looking at it, is you can write your variables out front. So V2 will be equal to 2.00 liters. So you want to prepare, what you're preparing is a 0.25 molar NaOH from 1 molar. So the from is important. It's from 1 molar. That means, M1. That means M1 is 1 molar. That's where it's originating from. That's the original, what we call stock solution. And then M2 is going to be what you're making from it. So you're making a 0.25 molar from a 1 molar. So it's going to be 0.25 molar. And then your V1 is what you don't know. So you can do 1 times V1, so basically V1 equals these 2 numbers multiplied together. Sorry, V1. 0.25 times 2, which is 0.5. So V1 equals 0.5 liters. So what that means is in order to create the solution, you're going to get 0.5 liters of your 1 molar NaOH, and you're going to make the final volume 2 liters by adding the remainder, which is 1.5 liters, to your original 1 molar solution, which will get you a 0.25 molar solution. So if they ask you to say that in words, that's what you would do. Here's an example of that from the second one. You're going to add that much to the stock, and then you're going to fill it with water to make it 2 liters. Any questions on that? Okay, next is the type of chemical reactions we're going to cover. And there's 3 main types. There's precipitation reactions, acid-base reactions, which we should have the gist of already. And then there's a new one called oxidation-reduction reactions, where instead of ions being switched or hydrogens and hydroxides being flipped, you're going to have electrons that are being moved from one atom or one element to another element. So that'll be interesting. We'll learn about oxidation state as well. So the first type of precipitation. Now, what does precipitation mean? Now, not like water precipitation like rain, but precipitate means an insoluble solid. Kind of, it's like the opposite of precipitation in weather. So if you have a solution with a precipitate, that means something that's insoluble. It kind of makes like a cloudy solution, or you actually see the crystals form. And the way you would have an insoluble solution is by having something that's insoluble in the solvent, such as an insoluble ionic salt. And there are a bunch of them, which we're going to learn in the next slide. We'll see the rules for that. But here's an example of a precipitation reaction. You have cobalt-2 nitrate, which as you name this one, cobalt-2 nitrate, mixed with sodium hydroxide, which is a strong base. So when you mix those, this precipitation reaction, what will happen is the anions will switch, or you can think about it as the cations will switch. So cobalt will switch with Na. Sure. And you'll have NaOH, and you'll have cobalt hydroxide, cobalt-2 hydroxide. Now, cobalt-2 hydroxide is actually not soluble, whereas both of the starting materials in the reactants are both soluble. So anything that has a sodium on it and anything that has a nitrate on it will be soluble. That's one of the rules. So when you switch them, however, the combination of cobalt and hydroxide becomes not soluble. So what will happen is they stick together and then they come out of the solution, meaning they become a precipitate together. And that's how you can get certain substances. That's a pretty important reaction, that precipitation reaction. And then you can balance it and you get the correct precipitation reaction. But in order to analyze a precipitation reaction, we're going to learn how to do, there's a thing called the net ionic equation, the complete ionic equation, and ways to analyze it and see exactly what's going on the ionic level. It really tells you, it makes you understand the molecular behavior of some of these ions. And in order to understand that, we need to concentrate on these rules. Now, this may seem like a lot. We'll go through each one right now. This list is basically the rules of soluble salts in water, of what is soluble and what isn't. So the rules vary from textbook, but they're all consistent. They're just in different orders. So we'll go over the first couple. This is not even that comprehensive. So what I'm gonna add things. So most nitrates are soluble. Wherever you see it's actually all. So all. So this is where nitrates are soluble. Wherever you see a nitrate, that ionic compound, soluble automatically. Very similarly also, acetates are soluble, H2C3O2 minus. Acetates are soluble. And before you ask, do you have to memorize this? To the best of your ability. But it's easy if you think about it correctly. So you just have to remember a couple of things. The first, nitrates and acetates are soluble. That should be the first thing you look over. If you see an ionic equation, you should be like, all right, is there any acetates or nitrates? If there are, then whatever that's paired with, the whole thing is soluble. Next, salts containing alkali metals. So meaning group 1A, lithium, sodium, potassium, cesium, rubidium, and also ammonium, which is a +1. these are all soluble as well. So if you see lithium or any of these paired with any anion, soluble. Right there off the bat, that's like 90% of what you're going to see. Not 90%, like 70% of what you're going to see for things that are soluble. Now, here's the insoluble. The most important thing about insolubility are these three elements: silver, lead, and mercury. So a lot of ionic compounds, unless they have nitrate and acetate, and that's about it. Yeah, so except acetate and nitrate, if you have silver, lead, or mercury, chances are it's going to be insoluble. So if ever you see those, that should be a red flag and be like, oh, something's insoluble there. So mercury, lead, and silver. Actually, lead and silver are the main ones. Mercury, I've seen it maybe once, but usually they're going to throw in questions with lead or silver as being insoluble. Most sulfates are soluble. Exceptions, you have, oh, look, there's lead. Oh, there's lead and there's mercury. But you have barium, which is one, and calcium, which is another. So the way we would look at these, and there are rules. So hydroxide, let's go over them right now. So hydroxides are only slightly soluble. So most of them aren't. But important soluble ones are the ones that conflict with the first rule, right? If you have or second rule, if you have a hydroxide that has group 1A, meaning the alkali metals, sodium, potassium, and then even if you have some of the 2A, such as barium, strontium, and calcium, that makes their solubility a bit better. So, and also that's a weird rule. They're slightly soluble. So like I said, with polarity, it's a kind of a spectrum. And the same thing with solubility of salts. It's kind of like a spectrum. It's not really yes or no. It's not that binary. But you'll see this isn't as bad as you think. Then sulfides, carbonates, chromates, and phosphates are only slightly soluble, except for those containing cations in Rule 2. So what you're going to see, I'll tell you right now, in these equations, you're going to have four ionic substances, the reactant sides, and then the product side is when they switch. Out of those, from the first two rules alone, you should be able, by process of elimination, to tell what's insoluble. Based on, is there anything that's silver, lead, or mercury, or if it nitrates, acetates, or the group 1A metals. Knowing all that information should tell you, from doing a systematic analysis, which one's insoluble. So you don't have to write all this down now, but we will go through examples. Okay, so let's do an example. So let's predict what happens when you mix KNO3 with barium chloride. So potassium nitrate and barium chloride. So KNO3 plus BaCl2. I'm not going to write the aqueous states. Well, actually you do, but I'll show you later, whatever. So then you switch them. So it'll be barium nitrate. So Ba parenthesis NO3 2, because nitrate's -1, barium is +2, plus KCl. Yeah, okay. This is an interesting one. So let's see. Is potassium nitrate soluble? Hell yeah, super soluble, right? Potassium soluble and everything, so is nitrate, so that's soluble. Barium chloride, it's soluble, and the reason why you know is because they tell you. It's something you mix together, and it's aqueous, so it's soluble. Also, it's a group 2A metal, so they tend to be soluble. Barium nitrate, it's a nitrate, always soluble. KCl, it's road salt, very soluble. It's potassium. Boom. They're all soluble. So what the hell happens if they're all soluble? What do you guys think? Any thoughts? If you mix them together, what will happen? Yeah, kind of. Like, let's see. Good. So Alex is right. No precipitate. Obviously, there won't be any precipitate, but basically nothing happens. Nothing will happen. Nothing at all. Because when you mix things into water, especially when you're dealing with salts, you're not going to see these molecules form. These molecules will not exist. What will form is you'll have a soup of K plus, NO3 minus, Ba2 plus, and Cl minus. Oh, we gotta balance this first. Wait. All right, now it's balanced. So you'll have a soup of these 4 ions. And in no combination of plus and minus, these ions will form an insoluble compound. Therefore, the soup will stay as a soup. And that's it. When they do randomly bump into each other, and that bumping into forces the formation of an insoluble salt, that is when precipitation occurs. So let's do an example of that. And we'll go through these things. We'll go through, so we're coming back to these terms. So there's the there's the formula equation, the complete ionic equation, and the net ionic equation. You're thinking, oh, professor, too much. Okay, we'll do an example, and then I'll show you how to do those right now. So here's one that actually works. It's a precipitation reaction. So the formula equation, which is the main equation with everything written out as you've seen it before, balanced. So this equation, you have potassium hydroxide, soluble, right? Because it tells you right here, but soluble. Then you have iron nitrate, soluble. Potassium nitrate, we know is soluble because all nitrates are soluble. And then when you switch them, you have iron hydroxide. So that's not going to be soluble because by process of elimination, it's not. And also, it was one of the rules that the hydroxides in general are sparingly soluble with everything except for group 1A and some 2A metals. So iron doesn't count as that, and it'll be insoluble. So now that we have the equation, we can figure out this next thing called the complete ionic equation. Now, what this complete ionic equation represents, it represents the behavior of the ions in water. So what ions are going to be present and what things are not going to be present as ions in the solution, like throughout the equation. So just like I told you before that the ions occur in like a soup, we're going to represent that soup. And it's very important to understand the notation of it. So here we have the formula equation. Now I'm going to write it down and you can follow with me and then ask questions later I'm going to write the complete ionic equation. So this is 3KOH. It's aqueous. Therefore, if you put that into water, it will immediately split apart into its ions. And it will form 3K plus 3OH minus. That's what it will form. Because there's 3 of the whole thing. When they split apart, it'll be 3 of each one. Then the same thing with the iron nitrate. It'll be 1 Fe 3 plus, since this Fe is a 3 plus 3 NO3 minus. This 3 from the NO3 minus comes up to the front. And the reason why is because if you leave it at the bottom, there's no such, or that's suggesting that you have a molecule that's NO3 3. That's not a molecule. They're not bound together like that. When they're split apart into their ionic components of NO3 minus, or when iron 3 nitrate does that, it's just 3 NO3s. It's just 3 nitrates separately. So that's why we have to bring the 3 to the front, because it represents the 3 separate ions that are in the water at the end of the day. So now that reacts to produce iron 3 hydroxide. Now this is a solid. This is not soluble. It's precipitate. So we can't split it apart. That's not how it behaves in the solution. In the solution, it's still precipitate. So that's the precipitate. Plus the remainder, the 3KNO3, is still going to be soluble, right? It's very soluble. So we have 3K plus 3NO3 minus. That will still be broken apart into its ions. So this is what we call the complete ionic equation. I'll give you a second to write it down, look it over, and ask questions. Because there is a lot. And it's complete because it's really everything. It takes into account everything in the solution. Any questions on it? Anybody online? Any questions? Yep. Yeah, that's basically how it works. No. Okay, good. Oh, good. Awesome. Good. So now this is the complete ionic equation. Now there's another thing, which the next step of simplifying this is getting the net ionic equation. So what the net ionic equation is well, we'll look at the definition first. The net ionic equation, it includes those solution components that undergo the change. So only the things that undergo the change from reactant to product are the ones that are written in the net ionic equation. So it basically cancels out everything that's not used. And everything that's not used, it's technically still used, it's part of the reaction. Those are called spectator ions. So I'm going to circle those, or I'm going to highlight, I'll circle them in red. So spectator ions, let's look at 3K plus. On the right side, we have 3K plus. So that's a spectator ion. We're not going to need that. 3OH minus. There's no 3OH minus here. It's an FeOH3. That we need to make the FeOH3. Same thing with the iron. We need that. The 3NO3 minus, that's a spectator ion. It's not going to be part of our precipitate product. And then what's remaining is going to be our 3OH minus, Fe3 plus, FeOH3. So after we're done canceling out the spectator ions, we get our complete, or our net ionic equation. I'll put net ionic would be 3OH minus plus Fe3 plus yields FeOH3 solid. And technically it's correct to put the AQ next to all these other ones, but I didn't have room to do that. So this would be the net ionic equation. Kind of sloppy. That just made it worse. Okay, any questions on that? Pretty good? Good. Oh, these are not included. Yeah, that's part of this. Yeah. Yeah, so this is the net ionic. Good. So you're canceling out the spectators. Cool. So that's a fun process. So this is what the net ionic would look like when you include the AQs, like that. Okay, cool. So now we're going to move on. Next thing, the second to last thing actually, is acid-base reactions. So then we go to oxidation reduction. So acid-base. Now, these two guys, Bronsted and Lowry, came up with a definition of acid-base reactions, of acids and bases. An acid is a proton donor, and a base is a proton acceptor. And we kind of talked about how acids have a hydrogen, and they want to get rid of it. So protons and hydrogen ions are the same thing. So proton equals H plus. And if you think about it, all right, what's hydrogen? It's got one proton in the middle, and it's got one electron. And the one with a mass of 1 has no neutrons. So if you are making hydrogen plus 1, you're getting rid of the only electron it has. Therefore, the only thing in the nucleus is one proton. So we call H plus one proton. So that's why we say proton donor, proton acceptor. That's why we say deprotonate or protonate. It's just movement of hydrogen ions. Okay, so when you react acids and bases together, we get neutralization. And this neutralization, I'll write one down. Let's react HCl plus NaOH, a strong acid and a strong base. And what will happen is the same idea as a precipitation reaction, where there won't be any precipitate, but you can think about it as the cations will switch, or the positives will switch with each other and to make new substances. So you'd get NaCl, and you'd get HOH, otherwise known as water. And this is the case for every acid-base reaction. You get the creation of water, the H from the acid and the OH from the base, and you get whatever's left over, which is a salt, usually. So NaCl, magnesium sulfate, whatever the salt may be. So you get a different type of salt. So this is the neutralization reaction. And the acid part from the HCl and the base part from the OH combine to neutralize, because water is neutral, to make water. So then you can do this type of experiment that is very key Chem-1 experiment called titration, called acid-base titration. Now, acid-base titration, or really what titration means in general, is we're determining the concentration. Let's say you have two solutions. One of them you don't know the concentration of, and the other one you do. One of them happens to be an acid, the other one happens to be a base. There's a way to detect the neutralization of the unknown one based on putting a known amount or a measured amount of the known one. So based on that, you can do some stoichiometry and figure out, all right, how many moles of the known one did it take to neutralize the unknown one? By that amount, and by using that and the volume of the unknown, you can figure out how many moles of the unknown was in there and what the concentration of it was. So this is a very powerful technique for acid-base neutralization and really determining concentration of an unknown. So the way to do it is there'll be a point within the titration, meaning the point in which you're adding the known to the unknown, which the molar amounts will be equal, will be enough to neutralize it. And in order to detect that moment, since all we're adding in chemistry most of the time is clear liquids, you really can't, it's not going to like tell you by looking at it, oh, it fizzed, therefore it's neutral now. Even though you can technically do that, if you put an acid into a base, it will fizz. When it stops fizzing, that means it's neutralized. So, but there's more analytical ways of doing this, and that way is by an indicator. So an indicator is a substance that is added at the beginning. That's usually a dye. It's what we call environmentally sensitive dye. And this dye will change color based on the pH of the solution. So pH is a measure of the acidity or basicity of a solution. If the pH is 7, that's a neutral point, it will change color. If it's not 7, it won't change color. And the endpoint is where that point occurs of where the indicator changes color. So where you add the exact amount of the exact amount of the known to get a color change. And that's where you would stop the titration and you would see, all right, how much of the known did I use? You can see the volume and the moles, you can see the volume and the concentration of it to figure out how many moles you used. That many moles is the amount of moles neutralized. And then you can use the original volume of the acid to see how many, or what the concentration was of the acid. Yes. Yes. So requirements, whatever. So one of the indicators we're not going to be tested on this is phenolphthalein. When I first learned it, I would say like phenolphthalein. That's one of the common indicators. And when you put it into an acidic solution, it's colorless. But then once the solution goes over that threshold and becomes a little bit basic, it turns pink, and it remains pink. So when you neutralize it, so here's what's going to happen. You have an unknown acid in here. Then you keep adding, this is a burette, you keep adding slow, drop by drop, you keep adding the base. Over time, the indicator will turn pink, but then you mix this around, pink will go away, meaning it's not neutralized yet. You'll get to a point where you put enough pink, or you put enough base in there, enough base in there, and you swirl it and the color won't go away. This means the equivalence point has been reached. And your titration's done. So the endpoint has been reached. And you're neutralized. Cool. Yeah, so that's about it for acid base. Any questions on acid base? More conceptual, I know. Okay. Redox. So, redox. Now, oxidation reduction is a different type of equation, different type of reaction. And it involves the transfer of electrons from one substance to another within the same chemical reaction. So there's many examples of this. Combustion is one. That's the most common oxidation reduction. You have any kind of, well, I could say oxidation, but like rusting, tarnishing, things like that are examples of chemical changes that involve a transfer of electrons, which are redox. So combustion is the most common. And what this means, and here's examples, you could use Na plus chlorine gas makes NaCl. That is a redox reaction because electrons are being transferred. Electron from the Na is being transferred to the Cl, and that changes its oxidation state. So what does that mean, oxidation state? So this is one of the key concepts we're going to learn about oxidation reduction is the oxidation number. This is actually a lot of fun to determine the oxidation number of an atom. So they use the word imaginary, like really no one's defined it well. People say, the textbook says imaginary charge. I call it pseudo charge. It's very similar to the charge, but it just represents, sometimes most of the time it's the same as the charge, but not all the time. And you're going to see examples where it's not. It's kind of like the pseudo, I'll just say pseudo charge, would I make it simple? The pseudo charge is the charge, but represented in that reaction. It changes based on what reaction you're in. It could, at least. So pseudo charge, whatever. So there's rules for it, and we'll just skip to the rules. So here's the rules for assigning oxidation states. And every atom in a chemical equation will have an oxidation state. So first rule, atoms in an elemental form, it should say elemental form, are zero. What that means is if you have sodium as a solid, potassium as a solid, and it's just that one element by itself, it's zero. Also, it means gases or nonmetals in their elemental form are zero, such as O2 and ozone. They are considered in their elemental form because it's a molecule. There's no other, it's not a compound, right? There's no other elements in there. So that will be considered zero oxidation state. Same thing with this mercury, but anything alone. Monatomic ions are the same as their charge. This is where that pseudo charge comes in because it's just like mostly the same as the charge. So sodium, chlorine, fluorine, potassium, all the group 1A, 2As, they're all going to be the same oxidation number as their ionic charge. So group 1A will be +1, group 2A will be +2, for example. And chlorine, the halogens are mostly -1. But then it gets weird. When you talk about, all right, if that's the case, then it's the same. Not necessarily. Oxygen, sulfur, nitrogen, phosphorus, carbon, their oxidation states are variable. They change a lot. Because it's not, so since the reason why is because depending on the reaction, it's not clear cut what they do with electrons. So generally you're like, oh, nonmetals, they want to gain electrons. True. But for ones that have a lower electron affinity or lower electronegativity, like carbon, nitrogen, sulfur, phosphorus, they can be swayed in the other direction. They can be swayed to gain electrons. Or to lose electrons, sorry. So their oxidation state it fluctuates. It depends what else, if there's anything else stronger in the reaction. And you'll see what I mean. Next, fluorine. Fluorine's -1 all time. The highest electronegativity, it's always -1 regardless. Oxygen is always -2, except when it's in peroxides. So a peroxide is anything that contains an O2 2- thing, which you can see like the easiest one, really the only thing you can see is hydrogen peroxide, so I'll just draw that. So hydrogen peroxide is H2O2. In this case, the oxidation state for oxygen is -1, and for hydrogen is +1. And the thing about similarly to ionic bonds is when you add up the oxidation states of the elements involved, they're going to equal 0. Just like for ionics, it's going to be neutral. At the end, the pluses are going to equal the minuses. Same thing. So for H2, it's going to be 1 + 1, and for O2, it's going to be -1 and -1. So that'll cancel out. And then for hydrogen, it's always going to be +1, always. So with these rules, we're going to do a lot of practice, and then, in my opinion, it's pretty fun. And we're going to be done kind of early. So what we're going to do is I'm going to do the intro of chapter 5, just to, it won't be hard, just to explain to you so we get the ball rolling quicker next class. Because before the second exam, I do want to do some in-class review. I think that'll be helpful. So we want to finish the material. Okay, so assign oxidation states to all the atoms in the following. So here's the way I do it in terms of notation. Let's do CO2. So I draw an arrow underneath it. So what's the oxidation state of oxygen? Anybody remember? Good, -2. -2. So I just write whatever the oxidation state is of that element underneath it. Now, if that's the case, what's the oxidation state for carbon? Perfect, +4. Because you have 2 oxygens, each one's -2. To cancel that out, you have +4. Carbon is one of those ones that's in the middle that it could have a high oxidation state. It could be +6 even. It could be -2. It could be +1. It could be +2. There's a lot of, it could change basically. So we don't know. +4, it's commonly +4, but I've seen it as +6 before. And +2 even. All right, next one. So NO3 minus. Now keep in mind, this one, the total charge is not going to equal 0. This is nitrate, if you've seen it before. You've seen this before. So we're going to figure out the oxidation states of nitrogen and oxygen in nitrate. So just to know more about nitrate. Now the total charge, if it's -1. So we have to keep that in mind when we're determining the charge of, or the oxidation state of the other ones, of nitrogen. So oxygen, what's the state? Yep, -2 always, -2. Nitrogen, in this case, I'll let you guys do the math. So what is nitrogen in this case? Good, Angela and Harrison, good job. So +5. Good, the reason why, we have +5, we have 3 oxygens. Each oxygen is -2. +5 minus -6 or -6 is positive, is -1. So -1 is the total charge of nitrate. Therefore, all the math works out. So nitrogen and phosphorus, they tend to be +5 or +3. So just keep that in mind as well. But there are cases they could be minus. So like, I'll give you an example. pH 3. Let's do some examples, whatever. Let's just go crazy with this. Let's do 3 examples. Okay, let's do H2SO4. So O4, what's oxygen? -2, always -2. Hydrogen, what's hydrogen? Good, +1. Angela, thanks, you gave me numbers, awesome, good. +1. Sulfur. What would sulfur be in this case? Not 0. Good. Good job, Angela. +6. So it'd be +6. And it does take some time to look at this, but when you get better at it, it'll get faster. So reason why, you have 2 hydrogens, that's +2. Your sulfur is unknown, plus your 4 oxygens, which is -8, right? And it all has to equal 0. So you have +2 -8 plus something has to equal 0. So that something is +6. So sulfur is +6. I've seen sulfur as +2, +4, +6, -2. I'm not sure about it. It could be, it varies a lot, is what I'm trying to say. All right, phosphorus here, pH 3. So hydrogen is +1. What's phosphorus? Good, -3. Good job, Isaiah, -3. Awesome, good. Now let's do a different one. H3PO4. Oxygen, -2. Hydrogen, +1. What's phosphorus? I gotta think about that for a sec. I know. Good, Angela, +5. Lucas, good job saying that she was right. But yeah, +5. +5, awesome. So you see how there's 2 compounds with phosphorus and the oxidation state is completely different. One's -3, one's +5. So that goes to show you that it's more like a pseudo charge. It depends on what it's bound to. So good, I think we got the hang of it. We got rules and stuff. Here's some more practice you can do on your own. Well, you see the answers. Let's do this one. Let's do this. So, and this is an important case actually. Now, in the ones that we just did, there was clearly things that we knew based on the rules and things that we didn't know, and only one of them that we didn't know. So we can easily deduce that. But in some cases, you might have 2 of them where you seemingly don't know. Know. And in C, you kind of see that. You have NH4 HPO4. Oxygen you know is -2. Hydrogens are all +1. But phosphorus changes, as you saw, and nitrogen is also one of those that changes. So any idea on how you would figure this out? I'll give you a hint. Ionic.
-8 + 8. It's going to be 0.
Well, no, not necessarily. I see what your thought was, but yeah. Wait, say that one more time. No. So not necessarily, I'm not looking for the answer here, but how would you go about finding the oxidation state of nitrogen and phosphorus here? Good. Yep. Yeah. Split it up. Is that what you're going at? Or no? Oh, okay. Let's just say you said that. All right. Yeah, sure. Splitting up. So the answer is we've seen these before. We've seen NH4. It's ammonium. And we've seen HPO4 maybe. That's hydrogen phosphate. And those themselves are polyatomic ions that can be split up. So if we look at one NH4 molecule, we can find out the oxidation state of nitrogen. So NH4 is +1. Hydrogen is also +1. There's 4 of them. So what would nitrogen have to be? Good, -3. So I'm sure that's what, good. Oh, yeah, Lucas, yeah, -3. Let's just say you said that, -3. Because probably you didn't see the plus. But yeah, -3. So -3 for nitrogen. And then we do the same thing for HPO4. So HPO4, it has a 2- charge, HPO4. So, yeah, because H3PO4 and then H2PO4 is -1, HPO4 is -2. Yeah. So in this case, you have oxygen is -2, hydrogen is +1. So you'd have -8 plus 1 is minus 7, or it would be plus 7, but it has to be negative 2 total. So phosphorus would be what? Yep, plus 5. I just had a bunch of numbers. Yep, 5. Good job. So phosphorus would be plus 5 in this case. So that is a way to figure out the oxidation states when more than one element in the compound is not as apparent as it was in the other ones, where it's just process of elimination. So yeah, that pretty much covers it all. With that message, you should be able to figure out the oxidation state of anything. So we're going to use that now. Any questions on it before I continue? No? All right. Okay. So now let's look at definitions of what exactly oxidation is and reduction is. So it goes by this acronym of oil rig. Very important acronym. So oil rig represents oxidation. Let's put ox is losing. And I'll put red. Reduction is gaining. So what do you guys think that it's gaining or losing? It says it right there. Electrons. Okay. So I guess it's too late for you guys. But electrons. So when you have something that's oxidized, what that means is it's characterized by a loss of electrons. What that means is when you compare its initial oxidation state, so these numbers that we've been figuring out are the oxidation state. When you compare the number before and after, the number increases. It goes more positive. So it increases in oxidation state. That makes sense, right? If you oxidize something, it should increase the oxidation state. And that's a loss of electrons. You're losing negatives, in other words, gaining positives. And we'll talk about reducing agent in a second. But let's talk about reduction. Reduction is the opposite. Reduction is when you decrease the oxidation state. So that number is going down. Reduction, reduce, going down, decreasing. So the oxidation state number that we were figuring out would decrease from the reactants to the products. And it's characterized by a gaining of electrons. So reduction is gaining. That's where the rig, of oil rig, comes into play. Reduction is gaining. So does that make sense? Is there any questions on that? Okay, so now one step further, we're going to be seeing equations where we have both of these things going on at the same time. You're going to have oxidation on one part, or on one element, and reduction on another element. In order for this to happen, in every equation, both of them happen. So they have to, because if, let's say, oxidation, it loses electrons. If it loses electrons, the electrons have to go somewhere in a closed system. They can't just disappear. So they end up going to the substance that is reduced. And just similarly, the gained electrons from the substance that is reduced have to be gained from somewhere. And they are gained from the substance that's oxidized and loses those electrons. Another way you can think about it is if something is being oxidized, it is causing the reduction of something else. It's facilitating the reduction. It's acting like an agent of reduction, otherwise known as the reducing agent. That's what this term means. So if something's being oxidized, it is helping or facilitating the other one be reduced. It's a very seamless give and take, just like ionic compounds, where Na is like, I don't really want this electron. Fluorine comes around, I really need this electron. All right, I'll give it to you, no problem, you want it. Like, one man's trash is another man's treasure. Like, I don't need it. Here, you really, really want it. For some reason, take it, whatever, all good. Very low energy process. Same thing here. Oxidation, they want things that want to be oxidized, want to lose the electrons. I'm losing electrons, somebody take it. Oh, you want to be reduced? Take it now, go. And reduction is the opposite. I need to gain electrons. Who wants to give me electrons? Oh, you're getting rid of yours anyway? Sure, I'll take it. Very seamless transfer. So something that's being reduced, on the other hand, kind of facilitates the oxidation, meaning kind of persuades the thing that's being oxidized to get rid of its electrons. It's like, come on, give them to me. You know you want to. You know you don't need them. Take them. All right, fine. So or let me take them. That's what it's doing. So I meant to do this. So the reducing agent, so whatever's being oxidized is the agent of reduction, or helping the other thing be reduced. In other words, the reducing agent. Whatever is being reduced itself is the oxidizing agent. So it's kind of like a flip-flop thing. But so let's do examples. This is just more confusing. Here, we'll do this. So here's the kind of questions you'll get. You'll get a general redox equation, and you're being asked which atom is being oxidized and which one's being reduced, and which one's the oxidizing agent, which one's the reducing agent. So for your exams and for homeworks, here's how I write this notation of how I figured this out systematically. I'm going to go, just like I balance equations, just read it like a book and assign oxidation states. So oxygen, -2. What's lead going to be? Good, +2. Oxygen here, still -2. What's carbon? +2, nice. Now what about this lead? What is that? It's in its elemental form. Good, 0. So I said about elemental form, its automatically oxidation state is 0. Oxygen here, -2. What about this carbon? +4, good. +4. All right, so now I'll give you a second to write all that down. We have the oxidation states of every element in this equation. So now it's our job to compare what happens to the oxidation state of lead. It goes from +2 down to 0. So what I like to do is make a bracket like that. And we can say it goes from +2 to 0. Does that mean it's being oxidized or reduced? Reduced, good. So the way to think about reduction, the physical number goes down. The physical number is reduced. That's the easiest way to think about it. So here you have reduction. And if it's being reduced, then it is the oxidizing agent. And then you have the next one. We'll use rainbow. Carbon. Carbon goes from +2 to +4. Carbon is increasing, therefore it's oxidized. That's cool. It's oxidized, therefore it is the reducing agent. Reducing agent. So that's how you would figure those out, is first assign oxidation states to everything and then go through it systematically. Any questions on that process? And they're very similar. They're all very similar. There aren't going to be many that are difficult, more difficult. Some might have more products and reactants, but the premise is the same. Something else I should mention is sometimes it might not be as apparent. So other things that are characteristic of oxidation is we talked about losing electrons. We talked about oxidation state. Oh, actually, wait. No, never mind, everything's here. But something else that, actually something that's not here, is sometimes when you have things that are oxidized, you can characterize them as gaining oxygen. So for example, from CO2 to CO3, let's just say CO3 was a thing, even though it's CO3 2-, whatever. If you went from CO2 to CO3, this is being carbon's being oxidized, meaning it's gaining an oxygen. And you can see that by the oxidation states. It's just a further confirmation. So -2, this carbon would be +4. In this case, the carbon would be +6. And this would be -2. So the oxidation state increases, but that's also characteristic of a substance gaining oxygens. That's just another alternate definition. And then with reduction, it's not gaining oxygens, but it would be gaining, or it would be either losing oxygens or gaining hydrogens. Losing oxygen. So I would suggest write these down. So for the oxidizing, you'd be gaining oxygens because that makes sense. And whoever just asked a question in the chat, I'll get to you in a second. And then you'd be also characteristic of losing hydrogens. Oh, and yes, Lucas, another example. I'll do another example. Okay. So any questions on that concept? That it's also oxidizing is also gaining oxygen, losing hydrogen. And reduction is gaining hydrogen, losing oxygen. They're kind of antagonistic. Okay, let's do one more reaction example. If we find one. Here we go. Do this. So yeah, cut to the chase, it's a redox. Cool. Now let's solve it. Let's see what's being oxidized, what's being reduced. All right, magnesium. So what is the oxidation state of magnesium here? 0. Elemental form, 0. What about chlorine here? Good, -1. Hydrogen, +1. Nice. Hydrogen here. What's hydrogen here? I hear a lot of numbers. So elemental form, 0. Yes, it's in its elemental form. So anytime there's an element by itself, even if it's H2, O2, O3 even, that means it's 0. And then the Cl stays the same as -1. And what's the magnesium here? Good, +2. That's sloppy as hell. +2. All right, so now let's make our comparisons. Magnesium, clearly something's happening. It's goes from 0 to 2. What do you think? Oxidized or reduced? Good, oxidized. Online people, you should be helping out the people in class because they feel pressured because there's only 3 of them. I'm looking up and they don't really have many people to look up at. So good job, Isaiah. Oxidized. Nice. So this is being oxidized. The oxidation number is increasing from 0 to 2. And then therefore it is the reducing agent. And another thing is, if you come to class, don't feel like you have to answer the questions. Like, if I was undergrad, I wouldn't want to come to class if they were this size because I'd be scared that the professor is going to ask them stuff. So whatever you want to do, I just try to make a good, chill environment. But, whatever. So next, don't feel pressured is what I'm trying to say. Next, hydrogen, it changes from +1 to 0. Therefore, it is reduced, reduced, reducted, reduced. Good job, Lucas. Reduced. And then therefore, it is the oxidizing agent. Cool. So yeah, that's about it for that. So any questions on that? No? Okay. Cool. So let's do another one. This is the last thing. So which of the following compounds contains nitrogen with the highest oxidation number? Okay. So what's the oxidation number for the first nitrogen? Good, -3. Hydrogen is +3 here, since there's 3 of them, so it would be -3. What about NO2? +4, because there's 2 oxygens, -2 each. To antagonize that, you have +4, or oppose that, you have +4. Nitrogen here, not -3. You say -3? Not negative, but positive, right? You're thinking the chlorines are -3, you're right. But the nitrogens would have to oppose that, which would be +3. N2, 0, good, elemental form. Nitrogen here, +2, awesome. So then the highest one would be NO2. So this is a good example. You could see how nitrogen, the state changes so much. And I said before, usually I see nitrogen -3 or +3 or +5, but really it could be any of these. But I'm just saying what I've seen the most. And anything could be 0. So yeah, that's about it for that. So I'm going to end the recording.